Okay, let's dive into this. Welcome to another explainer. Look, if you're a physics student, maybe a backyard astronomer, or just an optics hobbyist, you already know that capturing a clear image of the universe, or even the microscopic world for that matter, is basically an endless battle against blur, right? So today, we're going to explore exactly how we engineer our way past the fundamental limits of human vision.
Now look closely at this light. It's beautiful, sure, but it perfectly illustrates our core problem. In physics, whenever waves of light encounter obstacles or squeeze through small openings, they don't just politely travel in perfectly straight lines. No, they bend around the edges. This phenomenon is what we call diffraction. And because that light bends and spreads out, it creates this fundamental blurriness, a literal physical limit to clarity that we absolutely have to solve if we want to truly understand the universe.
To get us there, we're going to hit 5 key steps today. We'll start with the meaning of resolution, then move on to Rayleigh's golden rule, the resolving power of telescopes, prisms and diffraction gratings, and finally, we'll wrap up with the resolving power of microscopes.
So let's kick things off with section 1, the meaning of resolution.
To lay our foundation here, resolution is really just the method we use to see objects that are super close together as distinctly separate things. Think about it. When you look up at two distant stars, your naked eye might just see one blurry blob of light. Resolving power is simply the optical ability of our instruments to essentially pull that single blur apart so we can clearly tell, okay, there are actually two distinct objects there.
Which brings us right into section 2, Rayleigh's golden rule.
Now, you might be wondering, how do we mathematically know when that blurry blob actually becomes two separate things? Visually, it looks exactly like this. Look closely at how the solid line, that's A, and the dotted line, B, overlap. These represent the diffraction patterns of two totally separate sources of light. Because of that bending light we just talked about, they aren't sharp little points. Instead, they're spread out waves with a big central peak and these smaller ripples fading out around them.
And this leads us to Rayleigh's criteria. It's basically the universal standard of resolution. It tells us that two nearby images are just resolved, meaning we can finally tell they're two distinct things, if the central maximum peak of one wave perfectly coincides with the first minimum dip of the other. That's it. That is the exact threshold. Anything closer, they blend into a single blob. Anything further apart, they're clearly separated. It's a really elegant rule.
Okay, moving on to section 3, resolving power of telescopes.
Now that we've got our golden rule, let's apply it to the macro scale. Whenever starlight enters a telescope, passing through the circular opening or aperture of the objective lens, it actually forms a central bright disk of light surrounded by faint dark rings. In physics, we call this central bright spot the Aries disk. And to see two stars clearly, well, their Aries disks absolutely have to be resolved according to Rayleigh's rule.
Let's translate this math into reality, because this is where it gets fun. The resolving power of a telescope relies on this simple fraction, where the aperture, the actual diameter of your objective lens, A, sits right up there in the numerator. It's divided by a constant, 1.22, and the wavelength of light. But the absolutely crucial takeaway here is that numerator. Because it's on top. If you want higher resolving power, you literally just need a bigger aperture. This is exactly why astronomers absolutely must build massive, sprawling observatories with incredibly huge lenses. It's the only way to see clearer, sharper images of the cosmos.
But, as with all great engineering, there's a catch. The universe just doesn't hand us infinite clarity for free. As we increase the diameter of that objective lens to boost our resolving power, we unfortunately introduce a pretty serious problem called spherical aberration. Basically, this is a distortion where light rays hitting the outer edges of that massive lens don't focus perfectly. It makes crafting these giant astronomical lenses unbelievably difficult, not to mention insanely expensive.
Let's pivot a bit for section 4, prisms and diffraction gratings.
So let's shift gears from looking at distant stars to exploring how we resolve light when we actually want to split it apart to see its underlying spectrum. Think of a prism breaking white light into a rainbow. For a prism, resolving power basically signifies its ability to form two separate spectral images from two neighboring wavelengths. Its resolving power relies on its base thickness, multiplied by how the refractive index changes with the wavelength. Essentially, the actual physical geometry of the glass itself determines how finely it can pull apart two very, very similar colors of light.
Now, we step up from simple prisms to diffraction gratings, which basically do the exact same job, but with just immense precision.
Transmission gratings are made by drawing equidistant parallel lines on transparent glass with a super fine diamond point. This allows light to transmit right through those tiny clear spaces. Reflection gratings, on the flip side, have those exact same lines drawn on silvered mirror surfaces, which then bounce the resolved light back at us. To truly appreciate the engineering here, just look at this number, 10,000. For scientists studying the visible region of the light spectrum, the gratings they use contain an astonishing 10,000 finely drawn opaque lines per single centimeter. No way, right? But that is the level of microscopic engineering required to effectively obstruct and transmit waves of light. And the formula for a grating's resolving power? It is beautifully simple. A grating's ability to resolve neighboring spectral lines is simply the order of the spectrum, n, multiplied by the total number of lines obstructing the light across the entire grating surface, n. It's direct, it's linear. You want more resolution? You just add more lines. And finally, this brings us to Section 5, Resolving Power of Microscopes. All right, let's transition all the way down to the extremely small. When we look through a microscope, the mass changes just a little bit. Here, we aren't looking at angles up in the sky, we're measuring actual linear distance on a tiny slide. The physicist Ernst Abbe determined that the limit of resolution here is the least permissible linear distance between two microscopic object points where their images are still, just barely, resolved. To really understand Abbe's limit, you have to grasp this critical term right here, numerical aperture. What you really need to take away from this is the variable mu, which stands for the refractive index of the medium the light is traveling through. This literally means whether there is air, water, or a specialized oil sitting directly between your tiny specimen and the microscope lens, it fundamentally alters the instrument's power. Let's pull it all together into the microscope's resolving power formula. Notice what's happening here. The numerical aperture is sitting right at the top in the numerator, divided by the wavelength of light. This means if you use a medium with a higher refractive index, like say swapping out air for oil, or if you use a light source with a vastly shorter wavelength, you're going to be able to resolve vastly smaller microscopic details. It's honestly an incredible little hack of physics. So we've journeyed from the mathematical overlapping of waves to massive telescope apertures, all the way down to oil-immersed microscope lenses. Every instrument has its own specific formula, but they all serve one exact same purpose: fighting the blur of diffraction. But this leaves us with a truly fascinating conclusion. Since resolving power is fundamentally bound by the physical wavelengths of light itself and constrained by the physical size of the lenses we can actually manufacture, are there hard, impenetrable limits to what humanity can actually see? Just think about that the next time you look up at the night sky. Thanks for joining me on this explainer, and as always, keep questioning what you see.